Gilberto,
Sí, señor.
es que me dicen que están en espera varios los que están ahí,
Ya
pero no estoy seguro si están entrando a
están,
la sala adecuada o no.
están apareciendo.
Ya,
Ya entró
pero...
Luis,
Hola, hello.
pero,
Ok.
pero Alba no está.
Alba me dice que está en espera, a menos que se haya equivocado de enlace. Voy a decirle. ¿Mm?
Por eso te compartí el enlace de nuevo.
Qué raro. Qué raro.
Bueno, ¿me escuchan? Can you hear me?
Sí, yes.
Okay, nice.
Sí que está esperando, pero voy a mandar otra vez ahí el mensaje. Creo que está en otra sala.
Sí, seguramente. Compártele el nuevo, por favor.
Se la envié yo otra vez. Vamos a ver.
Gentiment laissé. Donc là, je me dis qu'il faut que je le jette. Oui. C'est quoi? Je sais pas. C'était pas les tables qu'on avait reçues, là?
Ya ingresó. Falta Carlos Beltrán.
Sí, allá sí te dejo a ti que lo
Hola.
llames. Ya estamos sobre el
Buenos días.
tiempo. Somos 3 minutos corridos.
¿Me escucháis bien?
Sí, perfecto. Muy bien. Muchas gracias. Estamos esperando a uno de los calificadores y ya comenzamos.
Dice que ya va a entrar.
Ok.
Hola Gilberto, hola Carlos, hola a todos.
Buenos días, Fabio.
Buenos días o buenas tardes para algunos.
Buenas tardes.
Okay. So just 2 minutes. We await another evaluator to start. So please.
¿Me escuchan, Carlos Jaime?
Sí, señor.
Oui, des fois, ça arrive qu'il y ait
Okay, thank you very much for coming today. Everyone heard me?
Yes, again.
Yes.
Okay, so thank you and welcome to the defense of Gilberto Javier. Today we will have the dissertation of the doctoral PhD thesis that the title is Memory Management in Software Quantum Computing. I am Fabio Martinez. I'm the current coordinator of the doctoral program. So I will manage this meeting. The idea, firstly, let me to present some rules to carry out the dissertation. First of all, Gilberto has around 45 minutes to present. And then the jury, every evaluator of the jury can ask the question as without limit of time. And the only person that can answer and respond this kind of question is Gilberto. After that, the jury and the Professor Carlo will meet together to define the deliberation of the current thesis presentation. So, Alberto, thank you much for the presentation, and you can start with the dissertation when you want.
Good morning, afternoon for somebody, esteemed professors and everyone present. Thank you for being here today. I'm Gilberto Díaz. I'm honored to present my PhD research entitled Memory Management in Software Quantum Computing Simulators. This work addresses challenge simulating quantum systems, focusing on memory optimizations strategies to support quantum computations. Let's begin by exploring the motivation and significance of this study. Quantum computing is an area of computer science that directly apply the fundamental of quantum mechanics to the way how computing is performed. Leveraging that concepts like superposition and entanglement and many others. Quantum computing, in theory, can solve problems considered intractable by classical computing, not by doing the work faster, but by doing less work. Several real quantum devices are available through the cloud and for selling from some enterprises. However, they still face important challenge like limited number of qubits, limited quality of the qubits, some problems in the connectivity, and operational errors. Therefore, quantum computing simulators running on classical computers have emerged as useful and powerful tools for testing quantum algorithms and concepts on idealized conditions. However, these simulations require vast computational resources, specifically memory resources. For example, if we are going to execute a simulation with a 50 qubit state vector, we requires about 16 petabytes of memory. The objective of my research is to propose some memory management strategies for quantum state representation and quantum gate operations. These strategies aim to optimize memory usage. Here, I explain briefly the fundamental of quantum computing required to accomplish this work, this study. Let's start defining a logical qubit, which is a unitary vector in a two-dimensional Hilbert space. It can exist in a superposition of basis states. That means that it can hold information that can represent multiple classical states simultaneously. A quantum register is a logical structure that holds and manipulates quantum states. In a software quantum simulator, we need to store the states per se and the amplitudes. Quantum gates are unitary operators that are expressed as unitary matrices with respect to a specific orthonormal basis. They are the mechanism for transforming quantum states. Another important concept we have to understand is how to transform a quantum state applying a quantum gate. We need to create this matrix U by performing the tensor product using the identity matrix repeatedly until we reach the target qubit. Then we apply the tensor product using the specific gate. After that, the tensor product is continued using the identity matrix until reaching the total number of qubits. In the end, a matrix of dimension 2 power of n times 2 power of n dimensions are obtained. In the state of the art, I reviewed several quantum simulators to study the technique used by them. Various aspects were taken into account to select the leading quantum simulators in the field. We take into account aspects like innovative features, adoption and partnership, academic and commercial use, community support, and open collaboration. A small list of the simulators evaluated here were Intel Quantum Simulator, Quantum++, Quest, QRAC, and QSync, and we revised the features like optimization techniques, hardware support, programming model, designing properties, unique features, simulation objects, and so on. I evaluated the performance of those quantum simulators using the quantum Fourier transforms because it is a very suitable benchmark algorithm because it's well studied and can be compared against analytical solutions. It performance scale predictable with the number of qubits, and it is an essential component of many other quantum algorithms. The platform used to execute the simulations were two nodes of the Cluster 1 of Supercomputing Center of Universidad Industrial de Santander, with these features, these specifications, and a workstation with an Intel Xeon and a NVIDIA GPU. The simulators were evaluated in two scenarios using shared memory parallelisms and GPU parallelisms. In the shared memory scenario, we evaluated these three simulators. The log scale helps to illustrate the difference between the performance of simulators. Intel quantum simulators exhibit almost a consistent upward trend and almost a linear behavior. Quest outperform all of the other simulators, and Quantum++ performance is consistent across all small and to intermediate qubit count, with simulation times increasingly slowly on the log scale for larger qubit sites. In the GPU scenarios, QSync outperformed Quest for small qubit count, and from approximately 20 qubits onward, Quest do better than QSync. In this part, I describe the core of the work I have done. Here, I describe several memory management strategies to reduce memory consumption. We start by selecting proper data structures. The first approach is to store the states using the binary form of the element of the state. However, for programming languages like C or C++, storing the state of a vector of, for example, 32 qubits, we requires about 128 gigabytes of RAM of memory. A better approach is to replace the binary notation of the element of the state vector with their integer equivalent. In this way, we only need, for a 32 qubits quantum register, we need only 16 gigabytes. On the other hand, we need to store the amplitude vector. It is comprised by complex numbers with real and imaginary part. Another promising strategy is remove the less probable quantum states. However, it introduces important drawbacks and risks like loss of fidelity. Let's understand fidelity as the distance between two states, the original state and the state after remove the less probable states. It is defined as the modulus power of 2 of the inner product of the two states. So the loss of fidelity is the ideal fidelity minus the fidelity of those states. It impacts negatively in the algorithm accuracy. It carries out error accumulation. We have to take into account the threshold sensitivity. It impacts also in quantum entanglement for some algorithms. Because the vector grows disorderly, every state must be, we have to execute a search procedure for every state each time we are going to use it in a calculation. To avoid the overhead and drawbacks introduced by state pruning, we create an array with all states sorted from the start by taking advantage of the array indexes. In this way, leveraging these indexes, we can avoid storing the state vector. So we can save this amount of memory. However, we need this full vector to store in memory. On the other hand, we can use a linear data structure in order to improve the performance. This work took advantage of the method proposed by Tuan True to achieve better memory management when a quantum gate is going to be applied to a quantum register. He states that we can avoid constructing this huge matrix by using a specific formula. This method is adopted also by Intel quantum simulators and many other simulators. To apply a quantum gate, a single qubit quantum gate to the KFB qubit of the state, we can apply the gate to the pair of the states whose distance between them is k bits. We can use these simple formulas to apply a quantum gate. Similarly, for a controlled 2-qubit gate, we can apply a similar formula. If we are going to apply a controlled 2-qubit using a control qubit on a target qubit, we can avoid to build that huge matrix. So, adopting this method, we can save this amount of memory. We also explore data compression in order to save memory. We studied the two leading data compressors today, which are lossless compressors and error-bounded lossy compressors. The first one is not suitable in this work because it produces low compression ratios. And the second one can be classified into two categories: the data prediction-based compression model and the domain transform-based compression model. The first one is represented by the popular library SC, and the second one is represented by another popular library like CSP. I did a comparison between them, revising their features like type of compression, primary use case, and so on. We have selected CSP library because it offers the following advantage. It is based on block-based approach, which means that the compression of the compression occurs in complete isolation from other blocks. It has a very simple interface, and it provides a good trade-off between compression ratio and precision. CSP has several operation modes. The most suitable for our use case is the fixed rate mode because the constraints are significant when we are going to save storage and we are going to deal with information transfer. Another strategy used here is using a distributed memory programming model in order to increase the amount of resources of memory. However, we have to take into account several aspects, like the node must have the same amount of memory, the division of the state vector or amplitude vectors must be exact between the nodes, and we have to take care using this relation to correctly distribute the amplitude and the state vector across the nodes. And of course, we have to take into account the impact of communications. In order to test these strategies described before, we have implemented a prototype of the simulator. And this part, we are going to mention only the most relevant aspect of this prototype in order to save time here in this presentation. The simulator was developed in C++ language. It was based on the quantum circuit model, and only the concepts of quantum computing required by this work were implemented in this prototype. It only used a single qubit quantum gate and controlled 2-qubit quantum gates. When we are using distributed memory programming model, we can find two situations: that the pair state is located in the current process or is located in a remote process. To find out the process number where the pair state is, we can follow this expression. This figure shows the distance between the state pairs involved in an operation with a single qubit quantum gate. For example, if we applied a gate, we are using a 5 qubit quantum state. If we applied a gate to qubit 0, the corresponding pair state will be located in a remote process. So if two processes are used, the remote process is 1. If we use 4 processes, the remote process is 2, and so on. To minimize, I forget to tell that if we send the results immediately, we are going to send this amount of messages across the nodes. So it impacts negatively in the performance because there is a large amount of communications. In order to minimize that overhead, entire segments of the amplitude vector are exchanged between processes. Calculations are performed locally on these segments, and the resulting data is then transferred and consolidated to finalize the computation for each process. In the case of controlled 2 qubits, there is not a fixed distance pattern between the pair states, so we followed a different and less efficient strategy. We create a temporal list with the remote ID of the process, the remote state, and the new amplitude. Once the loops of the calculations to apply the gate to the register, we synchronize all of the processes and send and receive the result. In the case of distributed memory combined with data compression, we avoid performing the compression and compression for sending and receiving data by leveraging some useful functionalities of CSP that allow serializing and deserializing compression vectors Although this strategy also introduced additional overhead, is not as high as the overhead compression and the compression upon sending or receiving. Now we will show the result of simulation using the different strategies studied here. This graph compares simulation times between state pruning and full state techniques. The log scale helps to illustrate the difference between the two approaches. In addition to the drawbacks that the state pruning introduced, like loss of fidelity and many others, having the state vector and amplitudes in a disordered manner introduce a significant overhead, which is observed here. Uh, uh, when we increase the number of qubits, the performance grows sharply very soon. Using full state vector, we can see a better performance of simulations. This graph shows the simulation time using OpenMP for parallelization. We can see here that the number of threads increases beyond a certain point, around 32 threads. For most qubit count, the simulation times does not decrease significantly. No substantial, that means that no substantial benefit from parallelism is observed for a small number of qubits. And we observe a better improvement in performance for the 30 qubit line. Here we are still using this amount of memory because we have to store the amplitude vector. This graph shows the speed out of OpenMP to observe the benefits of parallelism because there is not significant improvement in performance for a small qubit count. We show only the speed up for bigger number of qubits. For all qubit sites, we can observe here for all qubit sites that the speed up generally increases with the number of threads, reflecting the scalability of the implementation. For larger qubit sites, for example, for 28 and 30, we achieve higher speed up compared to smaller ones. This is because larger problems offer more computational work, allowing better utilization of parallel threads. This graph compares the memory usage of the full state and full state with data compression implementations. The CSP compression becomes more effective at reducing memory usage as the number of qubits increases. We can see here the difference. From 20 qubits onward, the implementation with data compression starts showing a noticeable memory saving comparing with the full state version. These graphs compare the simulation time of the full state and full state with data compression. Once again, the log 10 scale helps to illustrate the difference between the two implementations more clearly, especially for when the qubit count increases. This graph shows that CSP compression has a computational overhead that grows as the qubit count increases. For lower qubit count from 1 to 10 approximately, the simulation time for both versions are almost similar. From that onward, beyond approximately 10 qubits, the CSP implementation start to take noticeable longer than the full state only implementation. This graph illustrates the simulation time using MPI parallelization. For each qubit count, the simulation time decreases as the number of process increases. The reduction in time is not significant. It's most significant from 2 to 8. We can say that 14 processes. And for small qubit counts, there is not a significant improvement in performance. This graph illustrates the speed of simulation using MPI. Simulation with higher qubit count, for example, 28 or 30, show better scaling with an increasing number of processes. Lower qubit count exhibits limited speed up, flattening early. This graph shows the performance using a hybrid approach using OpenMP and MPI, combining those techniques. We can see that once again, the most significant reduction in simulation times occur from 2 to 16 processes. For higher qubit count, the simulation time still benefit from increasing the number of processes, but not so good as for a small from this range of processes. This graph illustrates the speed up of simulation using a hybrid parallelization. All curves are flattening around 32 qubits, indicating diminishing benefit from adding more resources. And we can observe that the hybrid approach outperforms MPI-only implementation significantly. This graph presents the performance using MPI parallelization with CSP compression. Similar to the uncompressed MPI implementation, the simulation time decreased from 2 to 16 processes. This is the most significant reduction in simulation time. And we observed a steep decrease in simulation process for qubit count, big qubit count like 28, 29, and 30 qubit. This graph illustrates the speed up using MPI with CSP compression. For a small qubit count, the speed up doesn't go far and flatten out quickly. For larger qubit count, speed up to scale well. This workload can better exploit parallel processing and the benefit of CSP compression. Finally, we can compare with other simulators the performance of our prototype. This is the graph presented previously, and we include our prototype here. From range from 1 to 18, 19 qubits, the performance is stable, is good. After or from 20 onward qubits, we can see a steep increase on the performance. However, we can see that it is not the best simulator, but it's not the worst. Upon completing this work, we can draw the following conclusions. state pruning, in spite of could be a good or a very promising strategy. It introduced a lot of drawbacks, and for that reason is not useful. On the other hand, it introduced an important overhead, impacting negatively on the performance of simulations. Initiating simulation with a fully loaded quantum register, we improve the performance. Although we have to use this amount of memory, we can save this amount of memory by avoiding storing the states. We adopted the method created by Don-True, which allow us to save this amount of memory. This is an important contribution, and using compression techniques, we can save up to 75% of memory. Also, we introduce computational overhead, which is justifiable in order to improve, to take advantage of memory resources, with possibility to increase the number of qubits. Adapting parallelism using MPI and OpenMP, we can improve performance, and we can mitigate the overhead introduced by compression techniques. So combining CSP compression with MPI parallelization is very effective, reducing simulation time for high qubit count. As further work, we can say that there are several areas remain for further research, like test other compression algorithms in order to look for a better trade-off between the compression ratio and accuracy, and create a protocol for efficient communication and synchronization between nodes. The scientific production during this work was 3 evaluator papers, one published in a Colombian journal, and other 2 papers publishing in a international conference, the Carla conference, and other one is still evaluating. I hopefully will be published in a journal of MPPI edition. So this is the presentation of my work.
Okay, Gilberto, thank you very much for your presentation. Now we open the section of questions. First of all, we invite to the jury members to doing the question, and we will start with the Doctora Alba Cervera Lierta of BSc of Spain to start with the questions.
Okay, thank you very much, Fabio, and thank you, Gilberto, and congratulations for your dissertation and also for your nice presentation. Thank you. And yeah, maybe I can start with some questions. I'm not sure if should I give all the questions all together, or just we will make different rounds with the different committee. What's the
One at a time, please.
Please.
No, yeah, one at a time. But I mean, should I ask one question, then another question, then another, or we will just?
Yeah. Yes, Dr. Alba, the idea is that you start and you can do all the questions in one block and then the second jury and so on and again.
Okay. So maybe the first question is, I mean, I'm a physicist, so I'm used to programming Python, not in C++ in general. So my first question is, why did you choose C++ instead of Python, for instance? Because there are many, so most of the quantum software languages that are being used, like the ones developed by IBM, by Google, by other companies, are use Python instead of C++. So I wonder why you choose C++ in particular.
Most of the leading quantum simulators, in spite of they have Python bindings, all of the cores are written in C, C++, I'm not sure, Fortran. So in order to have the possibility to uh, do a fine memory management, I choose C++ language. Uh, Now I realize that it was not the best choice. Uh, I think C is the best choice in order to have a good performance and to manage better the, the memory.
Okay. And related with this question is, will your simulator be used by a, let's say, a user, a higher level user that is programming in, I don't know, in Qiskit, for instance? So it's something that can be implemented easily, or you will need
Yes,
to do
is
some intermediate steps to put these two things together.
no, I developed not only the simulator but a library in order to use it in a high level in a high level way. It is similar in the instructions like Intel quantum simulators and quantum plus plus simulators and others written in those languages.
Okay. Then maybe we can move to in your presentation and also in your thesis, you compare your simulator with other ones, and in particular, it was not clear to me why your simulator doesn't perform as good once the number of qubits is greater than 20. So could you explain a little bit more? Why do you think that happens, or how can you improve that?
Yes, maybe the data structure is not optimized, and I think the scenario was a shared memory programming model. So maybe I have to improve the parallelisms applied in the prototype.
And with this performance, I guess the benchmark that you used was the quantum Fourier transform, right? You run.
Yes, you're right. Yes.
Did you try any other type of benchmark or quantum circuit besides the quantum Fourier transform, just to check that if this line of more than 20 qubits is always there, or it depends on the quantum circuit?
Yes, I try Grover, but Grover have a particularity at the beginning, and uh, it will it will take too much time to overcome that specific particularity, which is mark the state using a huge identity matrix. So I have to change, or I have to include, for example, sparse matrix management to deal with this part of the algorithm.
But that's very specific to Grover, so I wonder if you
Yes,
not
yes.
generate a random state or a random circuit with a few bunch of gates. So it doesn't have to be a specific application, but something that helps you just to test what is the performance of your simulator for arbitrary quantum circuits.
I tried small quantum circuits that not correspond with any algorithms specifically, and it was okay. I think the short algorithm could be implemented also, because the quantum Fourier transform is the first part of that algorithm.
Mm-hmm. Then in your conclusions, you mentioned that the future work or a continuation of your work could be trying other type of compression algorithms or other protocols. So could you elaborate a little bit more? What do you mean by that? So what other compression algorithms do you have
Yes, there is another techniques for compression. For example, wavelet compression, use it for image management. I would like to try that in order to see if the trade-off between the compression ratio and the accuracy could be better than CSP, and even try those compressors that preserve all of the data in order to see how the impact in the performance is.
Okay. And then maybe my last technical question is, you develop a simulator for the full state wave function, so for pure states. So I wonder if you can generalize it, or how would you do that if that's the case, for density matrix formalism? Because as you know, the simulation of exact vectors, it's interesting, but then the reality in the quantum computers is that they have noise, they have the coherence. So you need to use the density matrix formalism to really account of what is going on in the quantum computer in the real world, I mean, not in the simulation part. So I wonder if you can use your techniques of data management and memory management for implementing a density matrix quantum simulator. So did you think about that, or?
Yes, there is a lot of work to to make this prototype a full simulator. I think these specific strategies are not suitable for that density matrix. We have to apply, for example, a sparse matrix management in those cases, or even studying mathematically, like the method proposed by Don True, in order to see if there is a shortcut in order to avoid huge matrix in simulations.
Okay, I see.
So in that case, I will need physicists' help.
I see. No, it's a general question. Just wanted to know what was your opinion on how can you continue this work in that direction. So maybe I have a very last question, and this is a very general one, because you just defended your PhD. So I wonder, after all these years of hard working, what is the most surprising thing that you learned? Or it's a completely general question, but I like to ask this to all PhD students, candidates. So what is the thing that you enjoyed the most during your PhD? Something that you didn't expect it, and you
so
just...
surprisingly, and my answer is very raw, and the part maybe I enjoy it, but I suffer most was the mathematics. In order to implement the prototype and to understand how to save memory, I have to learn quantum computing. And my history, I have been very bad in mathematics. So it was my huge challenge.
So did this thesis kind of reconcile you with mathematics, or you still?
A little bit,
Okay.
not completely yet.
Okay. So, okay, I think that's it from my side. So thanks again for your presentation and for your thesis.
Thank you very much for your questions. Very interesting questions.
Okay. Thank you very much, Dr. Alba, for your questions. And the second jury member is the Professor Dr. Philippe Navo from Brazil. So Dr. Philippe is from UFLDS institution, and you can start doing the questions.
Thank you for the invitation. You hear me well? It's okay? Yes.
Yes.
So, very well, Gilberto. So let's go to my suggestions. I will mix some comments to improve your thesis and some questions. So some of my comments is to improve and to some corrections on your text. Very few, but I will include in this moment. So let's start. I'm going without an order of principle, and so I mix suggestions and looking for the page in your text. I received the text. I'm not sure that you changed the text, but it's the text that I received with the invitation. So the first comments that I have is in your abstract. I suggest you to include a sentence saying clearly what is the proposal of your thesis. You made an abstract that don't say at the final what is the principal point of your thesis. Second, I think it's yeah. So you have the possibility to hear after our meeting here all the suggestions. That is now registration. List of abbreviations. I suggest there's a lot of abbreviations on your text. I suggest to in the beginning of your document to have a list of abbreviations. Reference. You had some mentions without reference. As an example, you say that currently there are simulators that are going up to 60 qubits. So you need a reference about this. This is in the page 2 of your document or 6 in the total. Another reference is you say about IBM machine, and you say IBM brain, and you don't use reference about this. This is in the page 3 or 7. Okay. So let's continue. So as you say in your text, the objective of your thesis is to reduce it and made a memory management of your system, of your simulated system.
Try to establish memory strategies to reduce the representation of quantum states and for modifying or transforming those quantum states.
Yeah. Okay. Yeah. So it is important to say this clearly in your abstract. Okay. In the page 9, that is 5, No, 9 is the total of page, and 5, you have a sentence that is not completed. I hope that you correct this.
Sorry, Professor Philippe. I think you have the wrong version of the book. All of those
The
comments.
old version is the old version.
Yes,
Okay.
all of those comments were corrected previously.
Okay, nice, very well. Okay. And in
Because
page
that I
41, there
remember
is
clearly.
something that in page
I
41
remember
there
clearly
is.
that incomplete sentence. So
Uh-huh.
I correct.
Yeah, that is not complete sentence. Okay, did you correct this? Yeah. Okay.
Yes.
In page 41, there is something that is repeated. It's a figure, and it's repeated 2 times the figure in the text. No.
Yes,
Okay.
yes. All of those mistakes were corrected.
Okay. Hopefully. Well, let's go to some of the questions. About the simulator, why did you develop a new simulator? Why you don't use one of them and just work on it?
The revised simulators were the code were very hermetic. I don't know if that is the correct word. And they were full simulators, very complex simulators. And I realized if I use one of them, it will be very difficult to test every strategy studied here in this work and change many things inside them to test one of the strategies. So mainly that was the reason. It will take too long to work on one of those simulators that developed my own.
Okay. About your simulator, as you develop a new one, no, and if you look in your text, you will see that you just at the end of your text, you say that his name is TMFTS. It's just at the end. But
Yes.
yes, in my opinion, when you open the suggestion of simulator, you need to say, I was developing the TMFTS simulator. Okay. But what I suggest is that you have a table in the, I don't remember exactly, maybe in the chapter 2 or chapter 3, comparing different simulators. I suggest that you include your simulator with the evaluation of the comparison against the other simulator, or the other 5 or 6 simulators that you put in the table.
Yes, I did it at the end of the result chapter.
So you put the table now,
yes,
or not?
I did it by suggesting a suggestion of Professor Alba. I think so. Yes, he told me that I should include that simulator, and it is included as I show in the presentation at the end of the results. The graph comparing this prototype is not yet a simulator, a full simulator. It's a prototype against the others.
Okay, very nice. Another question. Why you use just the KFT algorithm to make the tests on your results? it will be not interesting to test with other algorithms.
Well, there is a small section telling why I choose that algorithm, mainly because it is a well-known algorithm. It can be compared against analytical solutions. It is simple, and it is an important component of other algorithms. For example, it's the first part of short algorithm.
No, I agree with you that it's a well-known algorithm. The only point is that when you work on just one, maybe there are some characteristic of this algorithm that work. So you are testing, and you say, "Oh, okay, it works well here. The performance is well this." But if you use another one, maybe it will be different. So it's better to work on 2, 3 algorithms, different algorithms, to have a better evaluation of the performance of your work.
Yes, I worked also on Grover's algorithm, but the
Yes.
results were not
Okay.
significant. So
The difference.
I prefer not to include it in the work because the results were not so good. So as
Okay.
I explained to Professor Alba at the beginning of that algorithm, there is a huge identity matrix, and I have to deal with that, and I couldn't find a precise or a good strategy to overcome that obstacle.
Okay. Another. It's just a comment. You say, I think, is in the conclusion that there's some memory limitation of the GPUs, and so it's why you don't use the GPUs and so on. But I think that things are changing very fast, and currently the GPUs have more memory, and each year are improving. It's important, if you continue to work on this area, to look for another.
Yes, I will. There is a lot of work to do.
Yeah, sure. So at the end of your work, that you look pruning, now state pruning and so on, because at the beginning, you when you read your thesis, uh, we had the idea that the state pruning will be one of the best solution. But after the end, you say, no, state pruning is not so well. It don't work so well.
Everybody, when I start to study this, everybody say state pruning up, state pruning down. Everybody say that. When I start to study that approach, there are many drawbacks on it.
Yeah. I agree with that. And so you say that compression is one of the solution with multi-nodes. But as you say, but compression is something that you need. I think it depends of the size of the things, not because you take time to compress and you take time to decompress. So you need to see if it is interesting, depending of the size. What do you think about this?
One of the reasons that I choose CSP is because it's based on blocks. We don't have to compress or decompress the whole data structure, but only the block where the element we are going to use is placed.
Uh,
So the overhead is not as high as other approaches.
so, and in your opinion, because at the end you say that with the compression you had something like 75% of improvement, and you don't say uh, about multi-node. With multi-node MPI, what is the improvements?
I showed the speed up graph and the improvement we obtained depending of the strategy from 12 to 50 speed, acceleration. Uh,
But
Another
around what is more important? This is the question. It's more important the compression or the multi-nodes or using MPI
no,
and so.
I think, and that's what I'm going to say after this discussion. I think using classical computers to do quantum computing is to combine uh, many technologies in order to gain good performance and good memory management. Uh, of course, I didn't work on GPUs, but combining MPI with GPU programming and compression, we can gain the best of both worlds.
Mhm.
Because even these compression libraries uh, have support for GPUs. They support many parallelisms approaches, but we can test and combine them and choose the best. I think combining GPU programming model with MPI and compression, we can improve the results presented in this work.
Okay. As a last question, I had some other points, but I would like to finish to not take a lot of time. I would like that you say something more about accuracy. In the beginning of your work, you say, oh, the impact of accuracy and so on. But at the end of your work, you don't say a lot about that. What this so this technique that you are using of compression and multi-nodes, what you think is the change the accuracy, maintain its change, and if change how much?
Uh, I did I did some experiments in order to to test the compression ratio and the accuracy.
Yeah.
Just let me show. This is a under the leaf slide. So from the compression mode of CSP I mentioned in the presentation, I choose the fixed rate because it's the the use case suitable for this work. So in this graph, I tried at 80,000 80,000 array, flooring double double precision array, and I execute some operation on them using different rates, 4, 8, 16, 32, 34, and these numbers mean that CSP will try to use 4 bits per value to store the compressed data. And here, of course, for a small number of bits, we are going to lose precision or accuracy. And of course, we gain compression, but we use a bigger compression ratio. We gain precision but lose compression. So I select the middle of the both work, obtaining with this value the number I presented at the end.
Mm.
As I said in the conclusion, there is a lot of work to do in that specific field.
I think so. I think
Yes.
that there is it's something that is important to take a look carefully. Okay, so thank you for the invitation. Thank you for your work. That we look that there is a huge hard work on it, and I also congratulate the thesis director. Okay, so
Thank you very
thank
much,
you.
Professor Philip. Thank you, Philip. Thank you very much, Professor Philip.
Okay, thank you very much, Professor Philip. Now we can go to the next member of the jury, the Professor Dr. Isidoro Dickler from CineStaff, Mexico. Professor, you have the microphone.
Can you hear me now?
Yes.
Yeah.
I've had problems putting the setup. Thank you very much for the invitation. It was a pleasure to work and read the work by Gilberto. I found that I'm going to do a little like Philippe did, and I have a lot of agreement with the people who were before me, with Professor Alba and Professor Philippe. I think still, or I don't know if I have the last version here. Sorry. If I have the last version, but I still found many repetitive paragraphs. For example, I find the ideas, what page is this? On page 14 to be repeated several times. And I think we had suggested that things were too repetitive. So I think it would be good to read it again. Or maybe we don't have the really last version. There's still some miswritings, use of plurals and singulars are mixed. So I think it needs one more reading to make it really nice and free of errors of that kind. I also find, and I agree with Philippe in particular, it's tough to find or where it is clearly expressed what the objective is and where are we going to arrive. I found it difficult. I would read it and then I would go on and on and on. And then I said, really, what is the clear objective? Is it said in words, but then when you go into the work, it's not so clear what's the port where we're going to arrive. There's also other applications that is interesting to know, like, I work a lot on combinatorial optimization, which is one of the fields that has been impacted strongly by quantum computing, since many of the problems are in MP and have been found solution in different of the models. And I think that's my very personal opinion, that the whole view is narrow. Maybe it's important to have made it narrow, as I think Professor Philippe at some point mentioned, so that you could advance, if I understand your explanation. But at the same time, I find that one would like to extract some general principles. I feel that at some point, things became so narrow that if I would like to use it not only specifically for what you have done, but if I would like to put one of my students, for example, and say, let's go on Gilberto's work and try to extract some general principles, it's hard. It's too specific in some parts to permit extracting these general principles. I also think, this is also very what I'm saying has nothing to do with the quality of your work. I think it's a very nice work. One could immediately feel that you have invested a lot of time, a lot of hard thinking, that you had to flow through a lot of mathematics that, as you said before, was not a field where you felt comfortable, but you did it. And that's very nice, and I congratulate you for all that hard work. But at the end, I think that the writing, or the way everything got resumed, became too narrow as to make that the work can be used in a more wider community, in the sense of people. There's a lot of interest in this work. People are working very hard to get these simulators, and I think it's made for very suitable, very particular situation. And you explained why, but I think it would be interesting to have some writing on how it could be used in other contexts. For example, being a mathematician, I would have loved that in the part where you talk very briefly about quantum computing models, in particular, you talk about, well, you mentioned topological quantum computer. There's a whole group outside interested in understanding and seeing from a much more computer point of view this. I mean, we're experts on braid groups, and it would be very nice to understand, at least with a paragraph and an orientation of where one could go and explore. Also, that there is a much more variety. I think comparisons were not enough or too few. I think it would have been interesting to have, although you did it, and that what gives value, I think we needed a little more comparison with other algorithms, for example. Understand, is this suitable? Or what is the complexity to move it to other algorithms? You mentioned now some, but it's not reflected in some sense, like some indications of where this can be used, what kind of problems it is suitable for. Do you think it extends naturally or doesn't extend? And one of the things I was asking myself is, do you think that your prototype can extend into a full competitive simulator, given that research in this area is fast? So I was just looking, because remember I told you that I felt that the reference falls short, that there's too much going on. and it would be interesting to have kind of an update of these things. So I just jumped into the computer again and started looking for last information on this, and a lot of things pop up. So then it's not clear where this work stands. I think because it's a prototype, you still have the advantage that you could move to try to accommodate the work and, I don't know how you say this in English now, abarcar.
Take into account?
Take into account something wider, not so narrow. So my question is, do you believe that this is extendable in some sense, or as narrow as it is today, it has the potential to really explode into a much more flexible system? Since my point of view is everything has been accommodated, so it works with your Fourier transfer model, it works with compression. Compression is a beautiful theme that has high impact in all kinds of fields. And there's a lot of things being developed. So I think one of the things that have to be mentioned more is what happens with different compression models. It's changing day to day. We're doing wonderful things in terms of compression. And it's not clear for me, where do you, in your conclusions, I would have liked to see a prospect of, you say there's a lot of research to do. I'm convinced that what you say is totally true, that this can be extended in many ways. I also agree. But what I don't feel is a guide of what you're thinking of. What are these lines, future research lines, developments that you could incorporate to your line of work that could take this to a next stage? I think the work is solid. You gave us a very interesting development. It's noticeable, the time that was invested, but I don't know, what's your opinion? Were you forced to this narrow view, or it was just a way to try and hit on the main topics without trying to open yourself to some more general principles going on?
Well, I would like to start or to make this prototype to an entire or a complete simulator, but it requires a legion of programmers or a legion of students, I think, for master students, in order to accomplish or in order to build a full simulator. It is possible. I think these are the basis for a competitive simulator, because none of the simulators studied so far considered compression. So combining both fields, I think, could be a good contribution for the area. Once again, we need more people interested in the area and interested in contributing to develop a bigger prototype or a complete simulator, considering, of course, all of the emblematic algorithms and maybe other algorithms not so popular. And of course, taking into account that it's difficult to move from one algorithm to another because they are very different, and applying this or any memory management strategy.
That's my point. Is that really true? What I mean is there no general principle that you discovered during your work that can be shared? Let's say we do what you said. We get a huge team of people to work on. We try to take this to a full-scale simulator.
We have to try every algorithm individually because they are very different. They use more memory. Some of them are more simple than others in terms of the data structure required to store what they need to work.
Well, that's the problem of my background. I always think that there's some general principles that can be taken so that you could say, nowadays, my scope is this, but with some work, with some team, with some collaboration, we could extend it to a wider scope. My problem is I don't read what's that wider scope. I cannot understand from the work. Let's say I want to collaborate with you tomorrow, and I'm in very specific things, and I cannot elucidate with how the information has been given to me if this is possible or not as a line of research that we would try together. I mean, I'm saying it very particular, but that's the point, that I think the writing or the presentation, for some reasons, maybe because it's very difficult really to put all this together, became in that sense too focused on certain techniques and certain models when we know we have a wider scope. Now, my general opinion is I thank you. I think it's an excellent work. I think it's very noticeable, the effort that was put. I do think in a second view, when you sit down and write the papers that you will write, it would be nice to be more careful in some of the ways things are defined, presented, and put. For me, it was difficult to, I mean, I know that you don't need it fully, but it would be interesting to have a much clearer view of the mathematics in some sense. You speak about the Hilbert space, what we do, but I think that there's much more in it, without getting very complicated, to make a nice presentation of the basic principles so that other people could use this work also to have a nice introduction to the theme. Because it's a nice work. I mean, you took the effort of going through the basic concepts and giving us a chapter on ideas, but all these things also are written in many books. So my point of view is, if you're going to give it to us, then it would be nice that that also had in some way a new form of giving me these topics that could be more suitable for a wider audience or for people more in the certain communities than if I go to a typical text.
I agree. Thank you. However, some recommendations made to me that we are in a public, in a group where this knowledge is almost well known, so I can make short that part. So and in the book is described in detail, more in detail. So the presentation, because the time, I have to make short all of those lovely concepts.
But that's my point precisely, Gilberto. Since you're not going to do what the book does, then I think it's too long as an introductory presentation of the basic concepts, because what is said is not enough to understand. You still, if somebody wants to read from scratch, would have to go to books if he doesn't know the concepts. And if you know the concepts, what's the case of having them there? What we want is to go directly and spend the time on precisely what is new, what you're giving as an aportación,
yes,
to the community.
Yeah.
And that's nice, because then you have more space to go and give us a better detailed description of what's new. It took me really, I agree, I never understood at the beginning what was your objective in a clear statement. I mean, we know what you did, but it's never said, from my point of view, in a clear way. So it was worthwhile maybe giving a very clear, not the general concept that, well, we're going to use a new simulator and we're going to use compression, and that's repeated many times, but in a more detailed, direct way. My line, what I did, what I implemented goes in this direction, and I think the steps forward are this and this and this, and we could go deeper on this. We had to stay at this level because there's no more information, no more techniques. We believe that things can be done in a different way and try to explain why. I mean, I think this work is a very nice work where you could find a lot of collaboration and there's many lines you could follow. It's a very well settled base for future research, I think. I congratulate you on that. It gives the main pinpoints, the main things. So in general, I'm happy that you invited me. It was a very interesting work to read, and I think you did a very good job.
Thank
but
you.
I do think you needed a more open.
Yeah, I think I was working on a small paragraph to include it in the presentation, but I was not happy with the paragraph, so I can work a little bit more on it and add it after, just right after the objective or the aim of the, in order to improve all of your, to take into account all of your comments.
For example, technology, computer technology is changing constantly and rapidly. We're having now computers much faster with many, many different things. What's the interplay between your prototype or the future simulator that's being developed and all these new computer, HPC computer developments? We're in a very, very rapid HPC changing world. And I cannot find a direct correlation between this. Is this going to become obsolete or it's going to explode, having more code capabilities? And that I did not find because from my point of view, I mean, the problem starts with that. This is a way of doing simulations of quantum computers, taking it into account the HPC infrastructure. And that infrastructure is changing very, very quickly. And it would have been nice to see if you have any kind of prediction, view of how this incorporates into that development. Because that happens a lot. I mean, there's so many branches of even mathematics, computer science and other things that could become obsolete because technology just went too fast. I don't know what's your vision in terms of your prototype or your future simulator in terms of these advancements.
I think, of course, it is difficult to keep the speed of the technological advance and parallelism strategies. However, these small prototypes and techniques developed here are not so influenceable. I don't know if that is correct. By the fact of how those technologies and research area go today. I think if I can build or yes, I can build a group of interested people on it. I can go rapidly to a good product, and it's not going to be obsolete so fast.
Okay, that's what I meant. So that maybe what you're telling me is that you do have a list of first principles. You're not technologically dependent up to a certain point. That's what you're saying.
Yeah, of course, yes.
Okay, thank you.
Thank you.
I think for me, for this moment, is sufficient. I congratulate you and I thank again the invitation for having the opportunity to read this very nice piece of work.
Okay, thank you very much, Professor Isidora. So the next one is the Professor Dr. Frederick McGee, from URCA.
Hello, yes, thank you, Gilberto, for this nice presentation. So there has been already a lot of questions raised by the members of the jury. Can you hear me, actually?
Yes, sure.
Good. So yeah, I'm quite agree with the what Isidoro and Philip raised, that the goal of the thesis was not clearly specified at the beginning, but that's we discussed a lot already. And for me, it wasn't clear what you were trying to do, especially you are presenting a work about memory management. And I see in your results a lot of plots about execution time, speed up, and things like that. And to me, it's more about the efficiency of your simulator than about the memory management. So that I would ask you, um, when you use MPI technique or OpenMP and things like that, how can you scale this over many nodes? How many nodes can you use? And finally, how many qubits can you hope to simulate in your system?
Unfortunately, I count only with 2 nodes of the cluster because we are running out of the infrastructure. I think with this prototype and these strategies studied here in this work, I could scale until 35 qubits and check how the memory saving is okay in terms of the trade-off between saving and performance.
Mm-hmm. Okay, so, and also what I would like have seen in your work is I know that you added a plot of a comparison of your work and the other frameworks at the end, but it's again a plot against simulation time. Yeah, figure 4.8. For example, you're comparing different simulators with yours. What are the comparison between the different strategies these frameworks are using compared to your approach to the problem?
I did the comparison using shared memory programming model with full state implementation. I didn't compare data compression implementation because the other simulators are not capable of that feature. So that was the scenario, the common scenarios in order to compare them.
Yeah, but if you compare your approach, so you are adopting a certain approach to manage memory. How do the other frameworks deal with this problem? Can you compare this? I know you don't have really access to these codes, but can you get some information about what are their strategies to deal with this?
No, yes, all of the Simulators mentioned here in this study are open source. I have access to the code, and all of them use the techniques mentioned or described in this work, like a full state vector and the method proposed by Don-True in order to avoid using a huge matrix when we are going to transform a quantum register. Uh, those aspects were the common aspects in order to compare them and my prototype.
Mhm. Okay. So you mentioned that you implemented some quantum gates, mainly 1 qubit and 2 qubits quantum gates. Is that true?
Yes.
Uh,
That's
is there any possibility to go to gates with three qubits, like Toffoli gates or things like that? Or is there some limitations? I know you're using
it is
equation.
possible. Yes, it is possible, but as I say to Professor Alba, we have to study a proper mathematical procedure in order to avoid to build a huge matrix. The the methods studied here only use single qubit quantum gate, a two qubit controlled quantum gate.
Yeah.
I think that was one of the point for future work.
Mhm.
I think yes.
So yeah, because you use equations 220 and 224 to simulate application of quantum gates on 2 qubits and 1 qubit. Is there similar work for higher order RET gates?
Uh, I'm not sure. I'm not sure because mature simulators like Intel quantum simulators uh, use those kind of gates also, and all of the others also. None of them have implemented three qubit gates or
Okay.
bigger qubit gates.
Hmm.
So I established my limit following the strategies considered by those simulators.
Hmm. Okay. Okay. And when you're comparing state pruning technique with the full state
Full
vectors,
state.
yeah, full state is uh, well, figure 4.1. So you're comparing again simulation time. So yes, we with state pruning we see that we're taking more time. Um, do you have any insight about the error you're doing with state pruning technique? Is there any way to quantify the error, or you haven't tried?
I wrote a small section where I described or I put an example how the error could be. Uh, However, I didn't took the errors results on it because I say somewhere that the nature of the algorithm doesn't allow that state pruning could be effective. For example, in Grover's and quantum Fourier transforms, they start or after a small number of iterations, they create a full state vector. So uh, studying the accuracy of this state pruning strategy, we need another specific algorithm in order better see the impact on the accuracy.
So maybe it's related to the previous comments about the use of the QFT algorithm to compare, and maybe that's also this error you're making using state pruning versus something else is also algorithm dependent.
Yes, yes, sure.
So yeah, so that means that is that meaning that whatever the technique you're using for memory management is it's also dependent on the algorithm.
On the nature of the algorithm. Yes,
So
that's right.
are we able to decide a broad strategy, or do you have to decide per algorithm what will be the best memory management strategy?
As I said, the conclusion section, I think the best strategy is the combination of compression and parallelism, because independently the size of the state vector and the amplitude vector, we can leverage the compression, and to mitigate the overhead, we can use parallelism. Um, Of course, if we use effect pruning, I think uh, uh, it will be an additional overhead, because we have to search every state every time we are going to use it in a calculation.
All right. Okay. So you said that you're not using GPUs at all.
No, I
No.
didn't.
So can you tell me again what was the limitation aside? That was because the memory in the GPU was not big enough. Was the
That was one of the arguments. The other one is an additional work uh, to have a GPU implementation of this prototype.
okay? And so maybe you know that there are new architectures of GPUs, especially the Grace Hopper GPUs from NVIDIA, which combine the CPUs with the GPUs on the same chip, and they share the same memory. Do you think you can rely on this kind of architecture to make your simulator more efficient?
I think we can leverage that kind of architecture, but we need to study uh, more in detail. And for sure, uh, we need to create a specific strategy to use it.
Mm.
This is a memory management in quantum computing depends a lot of the technologies and the nature of the algorithm.
Mm. So you mean that you will have to design something specific for this kind of architecture?
Yes, maybe. I'm just thinking about it, but I'm not sure.
Mm.
I have not used that infrastructure yet.
Okay. And so, and do you continue to work on the simulator even today, or
Hopefully, yes.
yeah? So maybe you may go to this kind of question on porting this the code to GPUs and this.
Yes, sure,
Yeah.
sure. You are giving me some directions to consider in the developing of the prototype.
And if you need some Grasshopper GPUs, we have some in RAM, so you can you can
Thank
come
you
here.
very much. Thank you very much. You are so kind. I will be happy to be there.
All right, so if I thank you again for this very beautiful work and for this nice presentation. Also for the revision of the manuscript after some comments I made, and thanks again for the invitation.
Thank you, Professor.
I think that's all for me.
Okay, Professor Frederick, thank you very much for the intervention. So we have finished the jury comments and questions, and we opened the section for the advisor team in this case. So I don't know.
Fabio, Carlos
the Professor
Beltrán.
Carlos, the Professor Carlos
The
Beltrán.
Professor Carlos Beltrán, sorry.
Yeah.
Sorry, Professor. Well, the next one is the Professor Carlos Beltrán from WIS Colombia. Professor Carlos.
Okay, excuse me. Gilberto, two questions. The first, how depend the pruning with the error parameter in your test? For pruning test.
The first consideration is the threshold. I set the threshold to the minimal representation of the numbers in the infrastructure I use it. Once again, the nature of the algorithm didn't allow prune any states. The only with random and normalization initial states is useful. However, is not the best strategy. So it is only for testing the strategy, but not it's not it's not useful strategy because the nature of the quantum Fourier transform and Grover's algorithm.
Okay, and about the quantum Fourier transform, what is the function that you use it to evaluate the quantum Fourier transform?
The function.
Sí.
I use the traditional algorithms. I can't show you. I think in the document it is described the quantum circuit, and in some point there is also the mathematical representation of the quantum Fourier transform. As I said at the beginning, I'm very bad in mathematics. I cannot remember the expression, so you can find it in the document.
Okay. Continue with the error parameter. Is possible to define different values for error parameter and that you evaluate the methods that you implement?
Yes, sure. It is parameterized, the threshold.
Okay. The result can be very variable with this parameter, or is the same in positive tests?
Yes, sure. Yes, yeah, and this is one of the biggest drawbacks of state pruning is you put it relatively so big, you are not going to prune any state, or if you put it small, you maybe prune a lot of states, and the distance between the original state and the state after pruning will be bigger, and of course the inaccuracy will be bigger.
Okay, no more questions. Thank you very much for you.
Thank you, Professor.
Thank you very much, Professor Carlos. Now we can close the section of jury committee, and we open the questions and comments that have the advisors. Let me introduce. In this case, we have a team of advisors. First of all, we would like to hear the professor, Dr. Jean-François Coutier, if you have some comments.
Hello. Do you hear me?
Yes.
Yeah.
I don't have the comments. I congratulate Gilberto for his work and thank him. It was a pleasure to work with him. Thank you.
Thank you, Professor.
Okay, thank you, Professor Jean-François. Now the Professor Luis Angelo.
Hello. Well, I believe it's quite Jean-François, Carlos. We know that it was a quite long thesis because we started before COVID. At the beginning, you were supposed to come to France, but then COVID comes out, and it was really hard to complete these things. We not always agreed because, for example, the idea of developing your own simulator was completely your idea. At the beginning, the idea was to try to use existing simulators and try to improve them. But at least for the matter of going deeper to how to compress information, how to check this, your simulator has proved to done things. Perhaps if you were using more traditional simulators, we could have done more examples of more things on GPUs, for example. But well, it was a PhD thesis choice, so it's still worth this. Always doing something worth to do. So after all, that's it. So I just hope that the jury likes your project, your work, and let's wait. So now pass the word to Carlos.
Okay, so thank you very much, Gilberto, for your thesis, and Luis Angelo and Jean-François for to support and to join us in this adventure. In real, the idea was to treat a current problem to use simulators, as Luis Angelo say. The first idea was to use the very known simulators, but in the development of the thesis, mainly for the pandemic situation, Gilberto proposed us to create another one. So it's for the reason that the jury is also wide, no? So we have people from physics, people from quantum computing, of course, people from mathematics, like the case of Isidoro, and a jury for the side of the HPC, that is the case of Filina Bot, and thank you very much. And of course, Alba, of course, I say we call it physics, but also is the expert in and with Frederick in quantum computing. So thank you very much. In real, for us, our interest is more for the side of the HPC support for quantum computing. So it's for the reason that Gilberto takes some of the decision, for example, with the use of some kind of language, or the idea of the C and C++ is more to be more close to the infrastructure for the system. In one time, the idea to use C++ is because he observed that there are some objects, so it is in a first time more quickly to make the development. But after, when he made more research, of course there are surprises, no? Like in the adventure of a PhD thesis. So it's a little the situation of the thesis. So thank you very much for all the journey. Real for us is very important your approach, your evaluation. And thank you one more time, Angelo and Jean-François. You know what is the next, Fabio?
Okay, thank you very much. So the next one is to to go to the deliberation. I invite to the jury members and also the advisor for the private section of deliberations and to define the final qualification for Gilberto.
Can I just raise a little thing? I would like to know, sorry that I think, breaking the protocol. Have you received any comments or opinions with respect to the papers published?
Yes, a lot.
Yes?
Yes,
It
a
has
lot.
had,
Yes.
so there is an impact already with the work.
Yes, indeed. I already respond in face of the Gilberto. There are different approach, no? Because there are different domains of the journals and the conference. So it's more easy when it's the people of the computer science, no? For the people of physics and mathematics, of course, there are a lot of questions because it's not. We had a real computer science approach. So for the reason the hybrid approach of this thesis, no? So it's more to how we can support quantum computer simulation in HPC system. And of course, there are another related question because around the quantum parallel theory, there are a lot of work. It's one of the ideas to maybe to develop another thesis because Gilberto made some basis points interesting to treat for the size of computer science.
Thank you very much. Congratulations on that. Sorry.
Okay. Okay. Thank you, Professor Isidoro again. Gilberto, because you are the owner of the meeting, can you generate a new link for the deliberation meeting, or can you generate a private room, virtual room?
Private room. I don't know how to do that in Teams.
Yeah, and then you can generate a new link of Teams and can share with us by
Okay.
chat.
I'm going to generate a new link for you and share with you and Carlos to share with the other
Members of the jury. Okay.
Yeah. Okay. Just give me a moment.
In the chat is more easy.
Okay. I will put it in the chat. Yes.
Yeah.
This is the link. It's already in the chat. I think.
Okay.
Fabio, try to get in and check. You can accept the other people.
Okay, now that I will join, probably I will leave from this meeting. So if anything happens, I comment to you with forward, right?
Hello, is there someone still missing the other group? Philippe Navo. Okay.
Hello.
No, hello, Gilberto. It's just I was looking because Philippe was not connecting to the other group, so I think he's posted here. So I'll go back to the other group. So,
Okay, okay. I thought it was fast.
okay, so let me see. See you.
Okay, bye.
Entonces esperamos un rato, ¿sí, Gilberto?
Sí.
Bueno, éxitos.
Gracias. Gracias.
Okay, I guess I came back properly.
Yes.
Yeah.
Yeah, yeah,
The first experience with Teams doing this.
Okay.
yeah. It's not really good.
Mhm.
We need Isidoro. Isidoro is coming, not
Yes,
yet.
he managed it as well.
No, but he was in, I don't know if it was in a telephone or in a tablet, so it's not
I think
perhaps
it's
not
in
the
a
same way.
tablet, I think.
So it's not the same simple way like us for us.
Okay, Isidoro is coming.
Yeah.
Yeah, okay, nice. Good.
Yeah, now we are complete. Yes.
We're all of us here? Yeah.
Yeah.
Yes.
Yeah.
So, Gilberto, I was in charge first to congratulate you because the jury has all decided that the thesis is approved and that we all recognize the quality and hard work you put in it. We feel happy that this has gotten to this conclusion. We have one little thing that it's important to mention, you and you heard before, is we feel that still the document needs a revision. There's several points we mentioned, all of us, at some point when we were gathered together, where we found things that were not clear, beginning from the abstract and the different chapters, the objectives. So we believe that it would be a very good idea, and this is mainly thinking in that your work is going to be read by a lot of people, and it's important that it's well communicated. It will have impact in new students, in other researchers. So a document that is very well written has much more impact than when people cannot pass through in a fluid way. So the recommendation is if you can rewrite the important aspects we mentioned and be a little more careful on some of them with a deadline of the 24th. Am I correct? I think we said 24. I'm not sure the date.
And for
January.
January, yes.
January 24. So that in this time, you're capable of seeing all the suggestions that were made and being very careful and methodic in trying to elaborate a final document, which can all of us feel satisfied with. We all think it's a very good work, but it really needs to be well written. And well written means that many important details be covered in terms of how they're explained, how they're written, the wording, making clear the objective, making clear many little points that if you look at the video, I suppose, of this meeting, you will see that some points came out. On the other hand, definitely we all decided that the thesis is approved. So it's just a question of handing out a document with the same quality as the work it has. Was I clear?
Your microphone is closed, Gilberto.
Yes, sorry. Thank you very much. Yes, I will work on it. In fact, I already start working on it. I expect that I will share the new version or improved version with you as soon as possible. I think I can do it taking into account all of your recommendation very soon. I have invited an artificial intelligence to the meeting, so I can have the transcription. It will be easier to attend your recommendations.
I think the
Very well.
speed is not so, sorry, speed is not so important. You have more than a month. It's really being very methodic in terms of covering all these aspects.
Okay, thank you.
Okay.
Thank you very much.
Congratulations, Gilberto.
Thank you.
Congratulations.
Thank you. Thank you very much.
Also,
Thank
even
you
if
all.
you have to work on the manuscript, take your time to celebrate this day.
Yes.
Okay.
I don't know how to say it in English, but un muy fuerte abrazo para ti.
Gracias.
Enhorabuena.
Gracias.
Enhorabuena.
Thank you
Okay.
for all
Thank you
your
very much, Professor, for
Okay.
all your
Abrazo a
collaboration.
todos. Gracias.
Gracias,
Felicitaciones
Gracias a todos.
también a los directores.
Bye.
Felicitaciones.
Que tengáis un
Okay.
buen día. Chao.